Hi, presenting Snap, Pursuit and Gain Virtual Reality Viewport Control by Gaze. The problem. In virtual reality, users look around by rotating their head or body. However, users may not always have the complete freedom to do so. For example, one could be in a public crowded area where it is socially awkward to move too much, or be physically unable to move about due to medical reasons. Perhaps it has been a long tiring day and the user just wants to laze about. Or it could be as simple as not having sufficient space to move about. However, all of these problems would be rectified if we were able to look around without moving. What if we were able to look around all 360 degrees in VR with only our eyes? The naive solution for that would be to just rotate the viewport left when one looks left and rotate the viewport right when one looks right. But it isn't that simple. Circuits are the ballistic movement that our eyes perform when looking from one point to another. The thing about circuits are that their movements are planned before it is executed, and we are unable to perform course correction mid-circuit. You can imagine it as a horrible GPS system that doesn't let you change its destination until you reach it. What this implies for the naive solution is this. Imagine that the black box is the field of view in VR, and this is the surroundings of the VR scene. Now, the user wants to look at the tree and a circuit is planned to move the eyes onto the tree. Oh no, because in the naive solution, we also rotated the viewport during the eye movement. From the user's point of view, the tree have also moved, resulting in the circuit missing the tree. While it is still possible to look at the tree, the user must perform a strange ping-ponging ritual just to look at it. Understandably, this will be very annoying. However, that is not all. What should we do if the head moves at the same time? The head generally works together with the eye to gaze at something. How about eye tracking limitations? What happens when there's distractions or noise or the scene being blurry near the edges of the headset? What about eye strain and comfort which affect eye movement and in turn our techniques? How about motion and simulator sickness which is prevalent in VR experiences? These are all design challenges we have to face when designing a viewport control technique via gaze. While I love to go into more detail, we will not have sufficient time for it within this presentation. Therefore, presenting our contributions. We present 3 new gaze-based techniques for viewport control. These techniques are hands-free while also allowing for head movement to be optional. In an abstract study, we found our techniques to be competitive with baselines in both coarse and fine alignment tasks towards known and unknown targets. We compare our techniques with 2 baseline techniques. The first is controller snap, commonly found in many VR experiences, which snaps in the direction of a button press. The second is head gain, which amplifies the head yaw rotation of the user. Our 3 new gaze-based techniques for viewport control are dwell snap, which snaps in the direction of a gaze dwell, gaze gain, which amplifies the combined head and eye yaw rotation, and gaze pursuit, which continuously rotates the viewport towards the direction of the user's gaze. More details regarding these techniques will be shown later. First, let's talk about the study. The study is slightly modified from a previous study about peephole pointing. In our study, participants first have to perform an alignment step by aligning the viewport to face directly straight ahead. Then, participants searches for the first target that will appear to the left or to the right of them. Next, participants rotate the viewport and align it to face the first target before selecting. This starts the task sequence. Following that, a second target will appear in the opposite direction. Participants must look for the target and select it. Participants would not have any prior knowledge of where this target would appear. Finally, participants return to the first target and select it. As this selection is the same as the first target, they would have prior knowledge of where the target is. This selection ends the task sequence. Note that all targets will have an arrow that will point towards the direction of the next target. This is to prevent participants from rotating towards the wrong direction and having to rotate more than necessary. Recall our 3 techniques, dwell snap, gaze gain, and gaze pursuit. Here, we can see the first-person view of the participant during the study. On his right is the top-down schematic view of the study. The camera in the center represents the participant in VR. The light blue region represents their field of view, and the dark blue circle is the alignment step target pillar that you can also see in the first person view. This means that for dwell snap, assuming the head is kept still, participants have to look at the revealed red region to snap the viewport in that direction. That is to say, if the participant is looking at the left red region, the viewport will snap rotate left, and if the participant is looking at the right red region, the viewport will snap rotate right. Shown here are the slowed down videos of our dwell snap techniques being used in our study. In the schematic view, the red ray, like before, represents the direction the participant is looking at in VR. The appearing circles represents the targets the participant must align the viewport to and perform a selection. Additionally, a semi-translucent overlay of the participant head in reality is shown in the center of the schematic view. Do note the disassociation of the virtual viewport rotation and the real-life head rotation that our techniques allow. Some of the design considerations dwell snap had were the balancing between the Midas touch problems against speed. The Midas touch problem in this case are the accidental viewport snaps that occur if dwell time to trigger the snaps was set to too low. We attempted to alleviate this by having a lower dwell time for subsequent consecutive snaps in the same directions, allowing for a higher dwell time for the initial snap. The boundary of the trigger region is also a concern. Having it too close to the center aggravates Midas touch, but having it too far from the center makes it uncomfortable and risks eye tracking inaccuracies. The second technique is the gaze gain technique. In gaze gain, instead of only amplifying the head like in head gain, we combine eye and head yaw is amplified. A transfer function then governs the viewport yaw angular velocity. A design consideration is that rotating the viewport fast during eye circuits results in missing the point of interest. But this technique has a unique feature of allowing one to circuit to something outside the current view. This implies the circuit was not induced by current stimuli, but due to spatial memory instead. This means for this specific scenario, we can rotate the viewport as fast as necessary. This allows for an interesting transfer function that looks something like this. If the y-axis is the viewport yaw velocity and the x-axis is the eye angle, there would be a threshold theta represented by the dotted yellow line. Under this threshold theta, it is more likely that a user intends to look at something in view and we have to limit rotation speed. But above this threshold theta, we can speed up and rotate as fast as necessary. The last technique is the gaze pursuit technique. The gaze pursuit technique rotates the viewport towards the direction of gaze, where the further towards the edge the gaze is, the faster the viewport would rotate. A small dead zone also exists in the center that will not induce additional viewport rotation. This technique can be vaguely imagined as a viewport that self-centers on what a user is looking at, where the point of interest that is being looked at will smoothly slow down and stop at the center. A design consideration we need to account for with this technique is that the technique encourages users to look closer to the edges to rotate faster. This results in an increased likelihood for eye tracking to get lost. Therefore, to alleviate this problem, we assume the eye is looking in the same position for a short time after eye tracking is lost. We investigated 4 independent variables in our study. They are the 5 viewport control techniques shown earlier. Then, there are the 2 levels of control, fine grain and coarse grain, representing the precision needed to perform a selection. You can imagine fine grain as using a laser pointer attached to the participant head to select targets, while coarse grain is attaching a flashlight instead. Subsequently, there are 6 amplitudes between targets, which represents the visual angle between the 2 targets as shown. Lastly, we have whether the participants have prior knowledge on where the targets will appear. When having a new unknown target, shown as B, it is the no PK condition, but when the participants return back to A, it is the PK condition. A summary of our results with 20 gender-balanced participants showed that our techniques were competitive to the baselines in speed, error rates, task load, and simulator sickness. This shows that gaze is effective for viewport control and is a genuine alternative to other head-only or hand-only techniques. We also found no significant difference in the amount of head or eye movement. This is surprising, but the data showed extremely high variances and we believe it is masked by individual differences. Lastly, Technique differences showed in error rate only under specific circumstances. This suggests that each technique has its own unique challenges. All in all, we presented 3 new gaze-based techniques for viewport control: dwell snap, gaze gain, and gaze pursuit. These techniques are accessible due to being hands-free and having optional head movement. We tested these techniques on coarse and fine alignment tasks towards known and unknown targets, and found them to be competitive in speed, error rate, task load, and simulator sickness compared to our baselines. This shows that gaze is effective for viewport control and is a genuine alternative to head-only or hand-only techniques. For more details, you can scan the following QR code to read the paper. That is all for Snap, Pursuit, and Gain, virtual reality viewport control by gaze. Thank you for listening.